Okay, hello everyone. So today I want to continue with modular arithmetic. Um, so there were some problems we didn't really get to cover last time, so I'd like to cover those and then also talk about some new things. So yes, the topic last time, I guess what we focused on mostly was this order of like if I have a number A and I have a number N that are co-prime, I can talk about the order of um, A modulo N. So how to think about this and how to use it to solve problems. So so I would like to start with just finishing the problems that we didn't solve last time. So that's these two. Okay, yeah, so let's start with the first problem. So it says you want to find all positive integers m and n so that you have this condition, 2 to the m minus 1 divides 2 to the n plus 1. Okay. We want 2 to the n minus 1 divides 2 to the n plus 1. So any ideas where we can start? Like, I guess there's a hint that we want to somehow talk about orders of an element modulo something, right? So,
I took them case by case, then I made a claim and proved that it does not work for any bigger than 2.
okay, so the conjecture is that m should be less than or equal to 2.
Yeah.
Okay, and so, okay, so you said you get step by step. So what's the first step?
Yeah, well, when m is 1 and belongs to natural numbers, we don't need to show that because 2 to the power of 1 minus 1 is just 1.
Uh,
When m is 2, it's 2 to the power of 2 minus 1, which is 3. So n
mhm.
has to be odd because 2 to the n, when n is odd, plus 1 is always divisible by 3.
Okay, so m equals 1 and 2, we can kind of do by sort of explicitly, we can just check. Okay, so what do we say? If m equals 1, um,
N is really anything.
n is anything, and m is 2, then yeah, you have to divisible by 3, and so you said it's what n should be even, right?
Odd.
Oh, odd, n is odd, okay. Okay, good. So those we can check. Okay, so great. So what about m more than 2? What can we do now?
I started by assuming that, no, first of all, it's clear that n has to be bigger than m.
Yes, okay.
Uh,
So we have n more than m.
so we can just write n as qm plus r, where q and r are the quotient and remainder.
Okay.
So then we can rewrite 2 to the power of n plus 1 as 2 to the power of qm plus r. After that, I split it to 2qm multiplied by 2r plus 1. And since my claim was that it cannot be congruent to 0, I started by showing that if I subtracted some numbers, I subtracted minus 1 and 2 to the power of r, and I got 2 to the r multiplied by 2qm minus 1. And that can be shown to be divisible by 2 to the m minus 1. And since
Okay,
I
I'm not following. So what do I do from, so I have, okay, I have this expression and then what am I doing?
I wanted to show that it cannot be congruent to 0 mod 2m minus 1.
Okay, we consider this expression mod 2 to the n m minus 1. So we consider, okay, 2 to the qm is 2 to the r plus 1. We consider this modulo 2 to the m minus 1.
Yeah, I
Okay,
wanted to show that it cannot be congruent to 0.
so claim is not congruent to 0. Okay, and why is that? Great. Okay, so
we
because
we can subtract 1 and 2 to the r.
okay, so first of all, I guess okay, this guy here um is you can write 2 to the m is just 1, right? So this is 1 to the power q times 2 to the r plus 1, which is just 2 to the r plus 1, right?
Yeah, so and 2r plus 1 can never be
Uh,
0.
okay, so I
So
guess it just follows, right? Okay, because 2 to the r plus 1, okay, so we should have r is between okay, so r is
split
less than
1 and between
yeah,
1 and m.
yeah,
And
okay,
this can never
so
be 0.
yeah, right. So it can never be 0 because yeah, so right, so yeah, okay, I guess 2 to the r plus 1 is between 2 to the m minus 1 plus 1 and 2 to the 0 plus 1. And neither of these will be 0 mod 2 to the m minus 1, right? Okay, so this works. Okay. I so actually I didn't realize this works. Okay, so this is a direct solution. Okay, that's very nice. Um let's think.
Uh, I think we can find a solution that is more easier than this. It's
Ah,
more
there's an
direct.
easy. Oh, okay, okay. So I thought this was very direct, but there's another. Okay, what's the other solution?
Uh, First, we note that m equals is the order modulo 2 to the m minus 1 of 2 to the n plus 1. I mean for 2.
You're considering the m is what? M is
Is
the order
the order
mod 2 to the m minus 1 of 2.
2.
Okay. Yes. Mm-hmm.
Uh,
Yes.
we have 2 to the n is congruent to minus 1.
Uh-huh.
Mod 2 to the m minus 1.
Is
And
congruent to
so
more. Yes.
to minus 1.
Mod 2.
And,
Yes.
and so we have 2 to the n is 2 to 2 to 2 2 to 2 to the power of 2 n is congruent to 1 mod 2 to the m minus 1.
Yes.
Um, so we have two cases. The first case that is 1 is congruent to minus 1 mod 2 to the m minus 1.
1 is congruent to minus 1
Mod
mod
2 to the m.
minus 1. Okay.
Or we have m divides 2n, but m does not divide n.
Okay. Okay.
The first case, we have 2 is congruent to 0, mod 2 to the m minus 1, and that gives us that 2 to the m minus 1 is either 1 or 2, and
Ah,
so
yes.
2 to the m minus 1 cannot be 2, so 2 to the m minus 1 is 1.
So we get 1, right? So there's only m equals 1 in this case.
In the second
And,
case, we should have m equal to, since m does not divide them.
and m does not divide what? Ah,
Um, or, or maybe you can't say that because
yeah, so you can do this and then what happens, right? So we say m divides 2n, m does not divide n. Um, does it mean, it doesn't mean m divides 2. I think it means 2 divides m, right? Is that right?
2 divides.
Because, yeah, for example, I mean, we can give a simple example. We can give like 6 divides 2 times 3. 6 does not divide 3, right?
Mm, uh,
So it's not quite.
Maybe we'll have maybe we can consider that M could not divide any prime that divides N, I think.
M cannot divide any prime that divides N. Not sure. Okay, let's okay, so let me make a comment about this problem. So when I first saw this problem, actually, I didn't realize you can solve it the way Adham had proposed. So I didn't know you can just do that. So that's very nice. That's very clean. So I actually had a different solution in mind. But now I'm just thinking, okay, this problem is the solution I had in mind is not very good. So maybe let's do something else. Let's do one of the problems that I labeled as homework. Let's do something similar. So problem 14. Okay, so it's a similar situation, but now you want to show that if M and N are so it's the same setup as before, but we now assume M is odd, and you want to show that the two numbers are co-prime. Okay, so it's actually a little bit even stronger, right? Because yeah, here you just want to show that you cannot have one dividing the other, but here you actually want to show that they're co-prime. Yeah, so let's think about this one. So maybe I can copy the problem. Okay, so good. Okay, so yeah, problem is you have M and N odd or sorry, our positive integers with M odd, and now you want to show that that they're co-prime. So any ideas?
Does the Euclidean algorithm works? We just want to show that the GCD is 1.
Yeah, so when I first see this problem, it reminds me of a classical lemma that I think we should know. So okay, if you have A, M, and N are positive integers, there's a lemma that says that the GCD of A to the M minus 1 and A to the N minus 1 is the same as A to the GCD of M comma N minus 1. Okay, so like for example, if I take GCD of 2 to the 10 minus 1 and 2 to the, I don't know, 82 minus 1, it would just be 2 squared minus 1. Okay. And you can prove it using, the proof is by Euclidean algorithm. So this is similar. You cannot directly apply the lemma, but it's the same kind of thing. So you can try to use Euclidean algorithm and let's see what happens if you do that. So Okay, so I think actually you can do it, but it's a little bit tricky. So maybe I'll leave it as homework because it's not really what I wanted to. Yeah, so let's just say homework. I think there's a solution with Euclidean algorithm, but okay. I think there's a solution with Euclidean algorithm, but okay, I'll leave it for homework. There's a slightly more direct solution actually in this case. If you think about orders. So, okay, so what are we trying to prove? We're trying to prove that these numbers are co-prime, right? But another way of saying that is that they have no common prime factor. So, like another way of just of phrasing this problem is okay,
So you just want to show that M is the order.
that M is the order.
Or maybe we can show that the phi function of 2 to the n plus 1 divides or is it the opposite? M divides the... Was it the opposite? Oh yeah, M divides the phi function of 2 to the n plus 1.
M divides the phi function of 2 to the n.
If
But
that
okay, what would
works,
that?
then M is the order. We can show that M is the order then.
Um, but okay, if this is oh, I see. But that shouldn't be true. And like M can be anything, right? Like I could make I could fix like 2 to the 100, like 5 plus 1, and then M can be some huge number, right? This can't always be true. Did you see like it's saying like for any M and N, right? Like
Yeah.
really, and yeah, it's kind of so okay. So okay, what you really need to do with this one is okay, you need some kind of perspective shift. So um what does it mean that two numbers are co-prime? It means that they cannot share a common prime divisor. So another way of phrasing this problem is uh let P be a prime, and then Mn positive integers with M odd. It cannot be that 2 to the m is congruent to 1 mod p and 2 to the n is congruent to -1 mod p. Like you cannot have simultaneously both. Does it make sense how it's equivalent?
Yes. If we suppose that such B exists, then we have 2 to the m minus 2 to the n. Maybe we can subtract these two.
Um, so um, okay, so someone like what is this really saying? Like what does it mean? Like these m and n have nothing to do with each other. What does it mean to say that there's an odd number so that 2 to the m is congruent to 1 mod p?
GCD m and b minus 1, 2 is the GCD of m and b minus 1 is congruent to 1 mod b.
Yes. But I mean, there's a more direct way of saying it, right? Like, hmm, like for which primes is it true that there's an odd number m, so that 2 to the m is 1 mod p? Um,
We should have that the order of two mod B is not even.
is odd, right? So exactly. So the somehow it's just okay. Okay, so like okay, so for fixed p, um, so there exists odd m such that 2 to the m is congruent to 1 mod p. This statement is equivalent to saying the order of 2 mod p is odd. These are exactly the same statement. Does it make sense? Why? Like
Yes.
like so if I have I mean okay if I have this, then it implies this just by letting m equal the order. But in the other direction, what is happening? If 2 to the m is congruent to 1, then m divides the then the order divides m. So order should be a factor of m.
There is a problem that we solved the previous session that says that if B is a prime, then 2 to the n is congruent to minus 1 mod B for some n equivalent with the order is the order is even.
Right. So yeah, this is equivalent. So there being a solution to the n is congruent to minus 1 mod p. So that equation having a solution, right? So this equation, 2 to the n is congruent to minus 1 mod p, has a solution if and only if the order is even. Okay. So this was a problem from last time, right? So okay, so now it follows, right? Like it cannot be that there's I have a prime p where there's both an odd solution to this and a solution to this, right? Because then the order would have to be both even and odd. Does it make sense?
Yes.
So yeah, so really this problem is actually just equivalent to this statement here. So this statement was something we did last time. And yeah, so yeah, the point here I guess is like, okay, this problem is phrased as something kind of complicated. You have to show that two things are co-prime, but when you understand it, it's really equivalent to this statement, right? Because what does it mean to show something is two things are co-prime? You show that they don't have any common prime factors. So it's about solving some of these exponent equations modulo p. Um, um, okay. So, all right. Maybe I'll say this. So for this problem, uh, maybe I'll say that. So okay. I think the better solution to this problem is the one that Adham proposed, but I'm gonna give now another solution which I think is okay. It's not as clean of a solution, but I think it's useful to understand. Okay, so let's do that. The problem we're talking about is this. So find all positive integers m and n. So 2 to the n minus 1 divides 2 to the n plus 1. So find positive integers m and n such that 2 to the n minus 1 divides 2 to the n plus 1. Okay. So what does it mean that this is true? So it means that, okay, in particular, it implies that for every, so it means that if 2 to the n minus 1 divides 2 to the n plus 1, it means that for every prime dividing 2 to the n minus 1, so this is a prime number, maybe call it p, you also have that same prime divides 2 to the n plus 1. Okay. Okay, so but okay, what does it mean? It means that okay, this is too complicated. Maybe we can just so this is actually maybe a little bit too complicated. I don't actually think it's that useful to understand. Okay, sorry guys. I think maybe it's this. Maybe I think I won't present that solution. I'll just I'll give an extra home for homework. Okay.
Uh, Doesn't it just imply that 2 to the power of m divided by 2 is equivalent to minus 1 modulo 2 to the power of m
2 to the power of
by
n
2?
divided by 2.
M.
Yes.
Is equivalent to minus 1 modulo 2 to the power of m minus 1.
Like this?
Yeah, I think it implies this.
Why?
Because we can say that 2 to the power, the order of 2 modulo 2 to the power of m minus 1 is and 2 to the power of n is congruent to minus 1 modulo m, so it should be congruent to m minus 2 modulo m.
Say it again. Say it again.
Yeah, it should be n should be the order plus something times the order plus the order divided by 2.
N should be yes. So n should be something times the order. Yes.
So the order
Divided by 2
divided by
times something odd. Like this?
Uh,
Have I understood it correctly?
yeah.
Shouldn't. Oh yeah, that's right. Okay.
Yeah, I think.
And the order is so.
Okay, so first let's just verify that this is true, right? So okay. Okay, so first of all, because there's a solution here, it means that n is it means that the order is even. Okay. And then okay, it means the order is even.
How do we know that 2 to the m over 2 is congruent to -1 2 to the m minus 1?
That's 2 to the what over 2? Sorry?
2 to the m over 2. How do we know that it's congruent to -1? Mod 2 to the m minus 1.
Yeah, so it's a good point because it's not prime, right? 2 to the m minus 1 may not be prime, right? So I think it's going to go like this. So it's because we know it's like this. So the argument has to go like this. So the argument I think will go like this. You have so we have that 2 to the n is congruent to -1 mod 2 to the n minus 1. So there's a solution, right? And we also know the order of 2 is m. So the solution will be one of these. Okay. And we know it's going to be like exactly there's going to be a unique solution here, right? Because otherwise the order would be smaller, right? Does that make sense?
Yes.
And we also know that if you took 2n, twice the solution, that would be 1 mod m. So that would have to be, in this case, the only thing it could be is m. Because 2n would have to be a multiple of m, and the only one that is in this range would be m exactly. Does this make sense?
Yes.
Yeah, so it has to be m over 2. That argument makes sense, yeah?
Yes.
Yeah. Okay, so that's kind of okay. That's kind of what I wanted to get out of this problem, right? Like, because you have a solution, you actually know exactly what it is. It's half of the order, and that means all the solutions are an odd number times half of the order. Does it make sense? Okay, yeah, so Karim, where do I go from here? So yeah, I have n as an odd number times half of the order. And okay, what from here do I do? Mm. Okay, so we have the order divided by 2 times the odd number. Okay, sorry. Then okay, we're just done because of this. This is impossible, right? Okay, that's the solution. Yeah, it makes sense. Yeah.
Yes, because 2 to the m over 2 plus 1 is between 0 and it's less than 2 to the m.
Yeah. Okay. Yeah. So this is the solution. Okay. Yeah. Sorry, I got very confused by this problem, but okay, that's it. Okay. Okay. Yeah, so let's continue. I think it's true, so I'll leave it maybe as homework because right now I'm a little confused about this problem, but I think you can even calculate for any m and n, you can calculate GCD 2m minus 1 and 2n plus 1 using some kind of similar argument. But okay, we'll just leave it. Okay, yeah, so let's go to problem 6. So what is the problem? It's this one. No, that's not that. Okay, so yeah, problem 6. So it's that if you have you fix a modulus, then and you look at the sequence. So what is the sequence? It's like a1 is 2, ak is 2 to the ak, like this. Sorry, ak plus 1 is 2 to the ak. So the sequence, it becomes eventually constant modulo n. Yeah.
I'm a bit confused by this because when I tried it, modular 7, it was not constant. I reached a repeating situation.
Okay, so what did you try? So we get mod 7, then what do we do? So yeah,
We
so how
have
do we
2 is 2 mod 7, then we just square it, which is 4 is 4 mod 7, then we square it again, and we get 16 is 2 mod 7, right?
So we don't square it each time. We take 2 to the power of. Oh, but it's not the same. Yeah, it's not. Sorry, if I do x.
Not the same?
No, because if I square it, it becomes 2 square, and then 2 to the 4th, and then 2 to the 8th, 2 to the 16, like this. Right, so I square it, I'm just doubling the exponent each time. But I don't want to do that. I'm doing something much larger.
Oh, that's not what we're doing.
No, we're not, because we want 2 squared, and then 2 to the power of 2 squared, and then 2 to the power of 2 to the power of 2 squared. It grows much bigger.
Oh yeah, that's why it didn't work.
Yeah.
Okay. I thought we were
But
just
also
squaring it every time.
But you also have to be a little bit careful, right? Even if I do this, so what, after 2 and then what, 2 to the 4 is 16.
16 is
And then
basically 2. 16 is basically 2, so repeats.
Why 16? Why 16 2?
Because 16 minus 2 is equal to 14, and 14 is divisible by 2.
So 16 is congruent to 2 mod 7, but what's the next term? It's 2 to the power of 16. So what's like 2 to the power of 16 is not the same as 2 to the power of 2 mod 7.
Yeah, but I originally thought that the sequence was just squaring itself.
I see. Yeah. Okay. If you're squaring, it's okay. You can reduce. But since I'm taking an exponent, I can't reduce it mod n. I have to reduce it mod phi of n.
I just noticed why it did not work because I understood the sequence wrong.
Yeah, but so like you have to reduce this mod 6 in this case, right? So you have to reduce it to 4 instead of. But yeah, okay. But even then, it actually won't work because you actually can't reduce it at all. I think that's it's not. It doesn't work like that.
I have a solution for this problem.
Okay, what's the solution?
So we're gonna be looking at Euler's totient function.
Yeah, right.
If we keep taking Euler's totient function again and again, it will be eventually 1 or 0, I'm not sure. And it will be constant. And when we're looking at this, we can actually take the let's start by the 2 at the bottom. We can take it modulo p, the 2 and then whenever we go up, we can take it modulo Euler's totient function of P, then Euler's totient function of Euler's totient function of P, and so on.
So what is P here? P is a prior or P is
Okay,
N?
no, actually, just say N.
Okay,
So
yeah.
we can take two modulo, the two at the bottom, we can take modulo N. When we go up another level, we can take modulo Euler's totient function of N. When we go another level, it becomes Euler's totient function of Euler's totient function of N, and so on. And this will eventually become one. And so all the levels we're adding up are basically the same since they're all congruent modulo one.
So there's a subtlety here, right? Because okay, so you're using the fact that if A is congruent to B mod phi of n, then 2 to the A is congruent to 2 to the B mod phi of n.
Yes.
Is this right? But it's not true. It's almost true. What condition do I have on A and B for this to be true? Or sorry, it's a condition on n. What condition on n do I have?
Oh yeah, N is yeah, I guess N is co-prime with 2. So N is
so
odd.
this is n if n is odd, right? It has to
but
be co-prime
I'm
with
pretty
2,
sure
right?
pretty sure we can just reduce the even. Yeah, we can just reduce the even cases to odd cases.
Yeah, it's true, right? So let's explain.
Just if it's to a power of 2 that's great enough, they'll all be the same module, the even part, and then you just have to solve for the odd part of n.
Good, right. So the point is, so when you say even part and odd part, maybe we should give. Okay.
Let's just say n equals 2 to the x times m, where m is odd. So if at some point all the terms in this sequence will have powers of 2 greater than x, and by the Chinese remainder theorem, we just have to solve for the odd part for m.
Great. Yeah. So the first thing we should do is we should say, okay, let n, as you said, equal 2 to the x times, say, d, where d is odd. Okay. So for k large enough, certainly 2 to the x divides a sub k. Okay. So it's constant mod 2 to the x. It's constant. It's 0 mod 2 to the x. So sequence is 0 mod 2 to the x. So then by Chinese remainder theorem, suffices to show sequence is constant, mod is eventually constant, mod d, remember d is odd. Okay. Great. And right. And so now you're saying I should look at it mod phi of d, right? So actually, there's a very clean way to state this argument, Karim. Do you know? Like you don't even have to consider like phi of d, phi of d. You don't have to actually do this.
How do you do that?
So you can say I go by strong induction. Do you just assume the statement for you assume that this proposition is true for all numbers less than n. So then you can just go by strong induction, right? Because it's true for everything less than.
You just take phi and it's less than n, and since it's true, then the powers are the same, are constant at some point. Yes, I get it.
Yeah, so I think that's the cleanest way actually. Then you don't have to worry about this phi of d, phi of theta. So it's very, so let's just write it down. So what it is, it's by strong induction. So let's see. So yeah, so let's see how this goes. Okay, so we just assume, so okay, let star be the statement. Assume star for all n prime less than n. So now what happens? Well, there's two cases. Case one is what? So case one is when you write 2 to the x, when you write n as like a power of 2 times an odd number. So case one is where x is at least 1, and then you actually are immediately done by strong induction, right? Because but you know, like you reduce it to showing it for d, but d is less than n. So done, true by strong induction. And then case two is when x equals 0. So like n itself is odd. Okay. And then it follows from star for phi of n, right? Because now I can really use phi of n because n is coprime to 2. Right. Does it make sense? Does the solution make sense? Can you guys hear me?
Yes.
Yeah.
Okay. Does the solution make sense, or should I give more details, or is it okay?
Yes.
Okay, great. Okay, good. So maybe we can go on. Yeah, okay. So next what I wanted to cover is how do you go from modular arithmetic modulo p to mod p to the k? So the first problem is lifting the exponent. So before I actually state what lifting the exponent is, let me say what the point is. So the point is actually something we covered last time. So last time we had this problem, which was, yeah, so you have 2, which, okay, so what is the order of 2 modulo 3? You can just calculate it, right? So the order of 2 modulo 3 was, you do 2 and then 2 squared, so it's 2. And then from there, you want to calculate the order modulo 3 to the n, or maybe 3 to the d. And what you find is that, or what we found last time is it's 2 times 3 to the d minus 1. As in every time you increase the exponent on the modulus, the order just multiplies by p. Yeah, so that's what we found. And actually, this is a general phenomenon. This is what happens in general. So let me say what it means. So if I was considering the order of say 10 modulo powers of 3, okay, so I want to understand like what is order of 10 modulo powers of 3. So let's start maybe with n equals 1. So if I just want to order mod 3, it's just 1 because it's already yeah, it's just 10 is 1 mod 3. And then what happens? So then I go to n equals 2. Okay, so this is a situation where, okay, when I go from mod 3 to mod 9, it doesn't multiply by 3, but it just stays as 1 because 10 is already 1 mod 9. Yeah, does it make sense what I'm saying?
Yes.
Okay, but now the point is, now if I ever increase the exponent again, so this is maybe I have to claim. So the claim is now, if I increase the exponent from here, so if I go to n equals 3, so mod 27, then the
Now it's
order,
3. It's 3.
now it'll be 3, right? And then if I go,
It's-
like if I go in,
It's 3 to the power of n minus 2.
yeah, that's the claim, right? So the claim is it should now be, if I take the order mod 3 to the n of 10, the claim is that it's 3 to the n minus 2. So like in general, once like, what is it like? Yeah. So the idea is well, okay. Before I state it, let me actually just state what the lifting the exponent says, and then it'll be clear like what it is in general, right? So lifting the exponent is saying the following. So it's saying that so I have a prime p, okay, and I have integers a and b. So probably the most common case you use this is like b equals 1, right? So like, all these problems b equals 1, but it works for general b. So you have a and b, so that a and b are equal mod p, and they're both co-prime to p. And then it says that if I look at a to the n minus b to the n, the amount of like the number of powers of p is what it is for a minus b plus what it is for n. So what I'm saying, okay, in this case, it's saying that I have, if I look at v3 of 3 to the of 10 to the n minus 1, this is going to be v3 of 10 minus 1. So there's going to be 2 powers of 2 coming just from n equals 1, and then however many powers of 2 are in, or powers of 3 are in n. Yeah. Yeah. So okay, so do you guys see how this statement is equivalent to these two?
Yes.
Okay. So please ask question. I can explain more, but okay, like the whole point is, you can use lifting the exponent to calculate some orders modulo prime powers.
But it doesn't work for the 2 case because 2 minus 1 is not divisible by 3.
Right, yeah, so it's not going to work for the 2 case. It's a good point. But what does work for the 2 case? So for the 2 case, what we can do is we can do the following. We can say, okay, I don't know the order of 2, but I know that 2 squared is 4, right? And I know the order of 2 modulo 3 is 2. So I can instead calculate the order of 4 modulo 3 to the n. And it's gonna be what? It's gonna be, in this case, 3 to the n minus 1, 3 to the n minus 1, right? Because 4 minus 1 just has 1 power of 3. And then I can use that to calculate it for 2, because did you see how, like, whatever the order is,
Yeah, because when we multiply, we add, and lifting the exponent.
but what I'm saying, okay, so what I'm saying is like, once you know this, you can calculate the order of 2 as well.
By induction?
It's not just, okay, it's not, okay, let me write it down, because actually I think there's something. So okay, so let's say I know that order of, okay, so assume that order of mod 3 to the n of 4 is equal to 3 to the n minus 1, which will follow by lifting the exponent. Okay, so now how do I calculate the order of 2? Well, the first thing is, okay, let's say this is k. I know 2 to the k is going to be congruent to 1 mod 3. Okay, so it follows that k is even, or maybe more precisely, like it means that the order of 2 modulo 3 divides k. Okay, so then I can write k is equal to 2 times L, right? So, and now what does it mean? I can look at 2 to the power of k minus 1 is really 2 to the power of 2L minus 1, which is 4 to the L minus 1. And so now, since I know the order of 4, I know the smallest L that will work is 3 to the n minus 1. Does it make sense?
Yes. We want to minimize
so-
L in order to minimize K.
Yeah, exactly. And you want to minimize the L, and since I know that, and so minimizing the L is the same thing as finding the order of 4, which you can apply lifting the exponent. Yeah. So you know, even you have this assumption that A and B are equal mod P, you can usually, if you do a little bit more work, you can sort of not worry about the assumption. It's not really that significant of an assumption. Like you can usually do some other stuff to get around it. Okay, so let's prove lifting the exponent, right? Yeah, so let's prove lifting the exponent. Do I have it anywhere? No, I don't. Okay, so yeah, so let's recall all the hypotheses. So I have P prime A and B integers. Okay, and the n is maybe positive. N is positive integer, right? Okay. Okay, and I need A and B are congruent mod P to begin with, and I need P doesn't divide either of them. Okay, and now what this will allow me to do is it allows me to calculate the valuation or the number of powers of P in A to the n minus B to the n, and it's going to be exactly the amount you get from A minus B plus the powers of P in the exponent. So how do we prove this? The proof actually it breaks down into two sort of simple lemmas, right? So basically you want to do some kind of induction on n, but how exactly do we induct? We want to induct on the number of powers of P in n. So let me write down the two lemmas that will imply the results. So lemma 1 is, okay, if P does not divide n, then Vp of A to the n minus B to the n is the same as Vp of A minus B. Okay, the first lemma. So it's consistent, right? Because if P doesn't divide n, then what? Then this term here is 0, right? This is 0, and there should just be equal. Okay. And then lemma 2 is like the inductive step, right? It's okay. It's that Vp of A to the P minus B to the P is the same as Vp of A minus B plus 1, right? So in that case, n is P, and so I get a plus 1 from here, and so okay, that's this. And then together, if I have both of these lemmas, yes.
So we do the induction on Vp of n.
That's right. The induction is on Vp of n, and you can see, right? So this is the base case. Vp of n is 0, and this is the inductive step. Make sense?
Yes.
So yeah, so let's prove the two lemmas. So for both lemmas, I mean the tool we're going to use is this. You know, there's the main tool, right? So what is the main tool for both of these lemmas? It's the identity, the geometric series identity that lets you factor A to the n minus B to the n as A minus B plus this geometric series term. And so this is the main tool, and okay, so let's see how do we use the tool to prove the two lemmas. Okay, so I can duplicate this page. Okay, so let's start with lemma 1. So lemma 1, we just want to show that if the exponent is not divisible by p, then the valuation does not change. So let's see. So I have a to the n minus b to the n. So I factor it like this. Right. I forgot to, sorry, it's very important. P is an odd prime. It's very important it's an odd prime. That I forgot to say this, but I think I said it in the statement. Yeah, it's an odd prime. You'll see later why it's important, but it should be an odd prime. You'll see in the proof. You'll see in the proof it doesn't work when P is 2.
Yeah, but there's also the case for when P equals 2. I'll
Yeah, so
send the
there's
Wikipedia link.
Okay, yeah, so it's also on the homework. One of the homework problems is to solve the P equals 2 case. But it's you'll see. Yeah, Kareem?
Yeah, it's useful.
Yeah, it's useful. It's useful, and you'll see here where we use the case that the fact that P is prime, and then when you do the P equals 2, or that you'll see when we do this why we need P is odd, and then you'll understand how to fix it for P equals 2. Okay, so let's do this. Yeah, so we want to understand the exponent of P here. So we know. Okay, so what it means. So from here we get exactly VP of A minus B powers of P. So what it really means is we have to show that the second term is not divisible by P, right? That's the whole point. So we want to show that P does not divide A to the n minus 1 plus A to the n minus 2B plus all the way B to the n minus 1. But it should be, yes?
We can substitute B is congruent to A mod B.
Yeah, that's right. So we want to use this one, right? We want to use this.
Yes.
And
we have
what does it tell us?
We have that this expression is congruent to n times A to the n minus 1 mod B.
Great. And 8, okay, n has A to the n minus 1 mod B. Great, yeah.
And since B does not divide any of them, so B does not divide this expression.
Great, excellent. So yeah, so P doesn't divide n by assumption, and also we also assume P does not divide A. So sometimes people forget this assumption. It's very important. But yeah, since we assume P does not divide A and P does not divide n, it follows that P does not divide this whole thing. This is not equal to 0. Great, so that's the base case. So now let's do the inductive step. Okay, so what is the inductive step? So, okay, so that was the base case. Let's do the inductive step now. Okay, so now we want to prove this. Okay. Okay, so yeah, we start off same way. We want to use the factorization that we know. And okay. No, like the last term is b to the p minus 1. Yes, okay. Great. So great. So from the first term, we get vp of a minus b powers of p. So we want to show that from here, we get only 1. So what we want to show is that in this case, we want to show that p divides the second term, but that it fully divides. So like it divides and p squared does not divide the geometric series term. Yeah. So this is what we have to show. We have to understand that p divides this expression, but not p squared. So, okay, to see that p divides the expression, it's kind of the same argument as before, right? Like once we have a is congruent to b, we can show that mod p, at least this becomes, this is p times a to the p minus 1, which is congruent to 0 mod p squared, okay? So only, mod p. So our only job is to now show that it doesn't vanish mod p squared. So any ideas how we can do that?
We have that b divides a minus b.
Yes.
So a minus b is either 0 or b mod b squared.
So it's not exactly 0 or p mod p squared. It could be p, 2p, 3p, all the way to p minus 1 times p.
Oh.
Yeah,
So
so it's not
must
quite...
be multiple of p.
It must be a multiple of p, yes. Okay, great. So with that, what can we do? It's the correct idea, right? So let's start with it, right? So before we said b is equal to a mod p, and that's what we substituted. We cannot substitute that, but we can do something similar. We can say b is congruent to a plus kp mod p squared for some k. We can do this, right? We don't know what k is, but we know b is of this form. And we can take this expression, and we can put it into here. We can see what this gives us. So let's try. Let's see what it gives us.
I think I have a simpler way of doing this.
Okay, explain.
We can just write it out as a to the power of p to the all to the power of whatever is left of the power we have, and minus. Okay, so we just
So
take
I
a to the power
I
of
don't
p
understand the
minus.
solution.
So instead of just taking a minus b, we can take a to the power of p minus b to the power of p. And then
we start here,
yeah.
you're saying. Okay, and then what?
No, what I'm saying is when we're trying to do induction, we can just take the let's say the number is the power is p to the power of x times so we take a to the power of p times x minus b to the power of p times x first, and then times the whatever is left of.
So okay, you're proposing we do a different induction?
Yeah.
Okay,
No,
so
it's the same, but
okay. So tell me what to write. Okay. I start with
so a to the power of p, a to the power of p to the power of times x, a to the power of p times x, to the power of x, a to the power of p to the power of x times
like this, yes.
yeah, minus b, yeah, equals a to the perf p to the perf x minus p to the perf p to the perf x, and we just multiply it by whatever's left.
Yes, I see. So it becomes m minus 1, a to the power of p to the x times m minus 2, b to the power of p to the x. And what's left? Okay, like this, right? So, okay, we will find that this one has no powers of p. We will find p does not divide this by lemma 1 even, right? But how do we deal with this term, right? Like the first term. It's equivalent to lemma 2, right?
Yeah, induction.
Yeah, so that's what we are trying to do, right? It's the this is the inductive step, yes.
Yes.
So I think we have to deal with this statement at some point, right? We have to prove this.
Yeah.
This I think is the main step. How do we prove this one, right? Because you want to show that okay, we get another power of p because of the factorization, but how do we show we don't get 2 powers of p, right? That's the main difficulty, I think.
Can't we just do A is congruent to B modulo P, and then we get A minus and then we get a to the power of p minus 1 plus a to the power of p minus 2 times b, and until this sum should be congruent to p times a to the power of p minus 1. Yeah.
We get it mod p, right? We don't get it mod p squared.
Okay.
So like one point is, okay, we could have had a is congruent to b mod p squared. Like if this term, right? So there's a situation that's easier to deal with, which is what if we had this one was not just 1? Okay, it's at least 1, we know by assumption. But if it's at least 2, then they're actually congruent mod p squared. So this equality here is true mod p squared. And so then we're done, right? Because then we know we get exactly 1 power of p. Does it make sense?
Yeah.
But okay, so if this is at least 2, okay, you can do that. But maybe it's not, right? The problem is maybe you have exactly 1 power of p here. Then you have to really think about how do I understand this expression and exactly how many powers of p you get. And so the thing I think, Karam, that you were sort of hinting at that I want to talk about is, well, let's think of, okay, we know a minus b is divisible by p. We don't know if it's divisible by p squared. So we know it's a multiple of p, modulo p squared. So we can write this. We can write b is congruent to a plus kp mod p squared. Yeah? And then we can try to put that into this expression and see what happens. And okay, so yeah, let's do it. So let's see what happens. We have okay, so we want to we know that we know a is congruent to, or not a, b. B is congruent to a plus kp mod p squared. And we want to understand a to the p minus 1 plus a to the p minus 2 times b all the way to b to the p minus 1. We want to understand this expression mod p squared, right? So what is it? It's going to be a to the p minus 1 plus a to the p minus 2 times a plus kp, okay, then a to the p minus 3, a plus kp squared, all the way to a plus kp to the p minus 1. And this is okay, it's all mod p squared. So, okay, it doesn't immediately look like anything got simpler, but I claim something did. So,
when we raise a plus kb to
yes,
some power, all those terms will cancel in the expansion because
exactly. So, yep, explain. Right. So as Karan was saying, right, when we take this a plus kp and we take it to a power, and we consider everything modulo p squared, most of our terms will cancel. Right. Let's understand. So m is just some exponent, but what do we have? We have a to the m. That's okay. A to the m minus 1 times kp times m choose 1. It's okay. But then all the next term is going to actually be 0 because we have kp squared, right? And everything else actually is going to be 0. So this entire, all of these terms that come after will all vanish mod p squared. So let me say mod p squared. Yeah, so and this vanishing is what really lets us move from mod p to mod p squared, right? Yeah, so let's see what it means. So each exponent it's not going to contribute to the full binomial expansion, just the first two terms. And what does it mean? It means that this sum mod p squared, it's going to be a to the p minus 1 and then a to the p minus 2, and we'll only have we'll have a plus kp. But the next term, we will only have, we will have what? A to the p minus 3, and then we'll have a squared plus 2 times, sorry, 2a kp, and then we'll have a to the p minus 4, a cubed plus 3a squared kp. And the last term will be a to the p minus 1 plus p minus 1 a to the p minus 2 kp. Yes. This right? Yeah, does it make sense what the expansion is? Did I make a mistake? No, I didn't think. I think it's okay. Yeah. Does the argument make sense, or does the statement and the argument make sense?
Yeah.
Okay. Okay. Yeah. So what is it? So what do we end up getting? So the okay, so in each of these guys, the first one is going to give a to the p minus 1, right? So we'll have a to the p minus 1, a to the p minus 1, a to the p minus 1, and we'll have p of them. So we'll get p times a to the p minus 1 as before. And we'll also get something else now, right? So something else we get is, okay, we can float out kp from all of them. So we get kp, and we can also pull out what? We can pull out a to the p minus 2, a to the p minus 2, a to the p, okay, we can call it a to the p minus 2. And what's the left? So what's left now is, okay, we'll get 1, 2, 3, and all the way up to p minus 1, right? I think we'll end up with this.
So it will be congruent to b times a to the b minus 1. Since
which one?
This the old expression.
Because the second term is also divisible by p, right? Because that's sum.
Yeah. Yes, because 2 is b is not 2.
Yeah, so here this is where we're using p is not 2. Yeah, so you see now this is why we needed p is not 2, right? Because we want to cancel the second term. We can only do this. So the second term cancels almost because the second term is what? So this guy is p times p minus 1 over 2. So if p is odd, then that's a multiple of p. If p is even, it's not. Okay, so here's where we need p is not equal to 2. So now since p is not equal to 2, we can cancel this term, and we just still have p, p times a to the p minus 1, which is not divisible by p squared. Okay. Yeah, okay, so it makes sense, yeah?
Yes. So now we how could we do the induction step?
So now how do you do induction, right? So the induction step is like this, right? So it's I think it's exactly what Kareem was explaining, right? So for induction step, okay, we take n is like this. So n is what? N is p to the x times m. So what do we want? We want to show you have vp of a minus b is equal to vp of, sorry, a to the n minus b to the n is equal to vp of a minus b plus x, right? So so what? So yeah, so this one is not divisible by p by lemma 1, right?
Yes.
Makes sense? So now you just have to understand this one. But this is repeated application of lemma 2, right? Because we know vp of a to the p to the x minus b to the p to the x is equal to vp of a to the p to the x minus 1 plus v minus b to the p to the x minus 1 plus 1. And we just repeat. Does it
lemma 1 says that if n is not divisible by b, then we have a to the n minus 1 plus up to b to the n minus 1 is not divisible by b.
Yeah.
But here n will be divisible by b. The exponent is divisible.
No, this statement here is lemma 2. This is the one we were proving here, right? So the lemma 2, this one.
Yes.
We are applying it to a to the p to the x minus 1 and b to the p to the x minus 1. And then, so it gives this, right?
Yes.
So, and then we keep applying, right? So then this is equal to vp of a to the p to the x minus 2 minus, okay, like this, and then plus 1, okay. And you just get 1 each time you multiply by p, yeah. Does this make sense?
Yes.
So it's induction, yeah. It's just lemma 2 you apply over and over again.
So we substitute a with a to the b, a to the b to the x, and b with b to b to the x.
Yep, that's right. Yeah, like this.
And we are using lemma 1 and lemma 2.
That's right. Yes. Yeah, so that's why I like to think of it as lemma 1 and lemma 2. I like to think of lemma 1 as the base case and lemma 2 as the inductive step. But you have to change what A and B mean when you do the induction.
Yes.
Yeah, but it's the same. Yeah, so any questions? Does it make sense? Okay. So here's what I'll do. So I get a bunch of warm-up problems, right? So I think, okay, probably you see how to do them. So what I'll do is I will just state the answer to problem 4, and then, okay, we'll just make sure we understand and we agree that's the answer, and then it can be homework to actually solve it, right? So yeah, let's just recall what is problem 4. So it's this one, right? Okay, so let me find a page that's empty. Okay, so let's put it here. So, oh, that's not that one. Oh, no, sorry, it's not right. Okay, sorry, I kind of lost the page. Okay. Yeah, so this problem 4, right? So okay, so what is it we want to understand? So we have P and we have A, so P is prime, and we know P does not divide A. And we want to understand what is the order of A, but this time mod P to the K. And we assume that we know the order of P mod A, and it turns out we need to know a little bit more than that, right? Because we saw that in the example here of 10, right? You need to not only know the order of A mod P, but you need to know that when you take A to the power of that order, you want to see, okay, you get when you get something that's 1 mod P, but you can also get some extra prime factors. So we see what is the valuation of that. Okay, so we need to know both of these. Okay, so let's call the first one K, and the second one, let's call it, I don't want to use K, so let's, okay, let's just say like this. So let's call this one maybe R or something, and this one we can call it D, okay? So D is the order, and R is the number of total amount of prime factors you get when we take A to the power of the order, -1. And so the statement that will be true, that I will leave it as homework, is that you want to show that when I take the order mod P to the K, okay, 2 things can happen. So if K is less than or equal to R, then it's the same as D, right? If I take P to the K, like K is less than R, I don't need anything extra, right? It's D. And if K is more than or equal to R plus 1, then it's D times, now I need powers of P. I take P to the power of K minus R plus 1, like this. Maybe minus one, right? Sorry, I'm a little bit confused. So is it +1, -1, is it 0? Right, so when K is R, it's D. So maybe just like this is what it is. Maybe like this. Yeah. Okay, so does it make sense what I wrote, or should I explain why this is the case, or?
Why it's true?
So okay, like what happened for 10, right? So like for 10, what was it? It was the order for 10. Okay, so like this. So so if I do the order mod 3, it's 1. And if I do the order mod 9, this is also 1. These are the first case. Yeah? Does it make sense? So like when like the order, does it make sense what I'm saying? Like that's this first case. Like for the first few powers of 3, the order won't change because 10 minus 1 already has some powers of 3. But then from there, it increases by 1 each time. Right? So from there, I'll have order mod 27 of 10 is 2. And so I mean, Karam, should I explain why these are true? Is from letting the exponent? Is that maybe what I should do? So what's it? I didn't mean to write 2. I meant to write not 2. Sorry, I meant to write. Sorry, the order is 3 and 9. Yeah.
So we have to find a way for when A is when A minus 1 is not divisible by P.
Yeah. So I'll yeah. Okay. But okay. Does maybe we can just do some. Maybe I think it's better to do some examples.
Because
Let's
if
just
it's
do
divisible
10.
by
Okay.
P, it's simply lifting the exponent here.
Yeah, but let's do both. So first let's do the case where it's divisible by p and it's not. Okay, so like if I want to understand the order um of 10 modulo 3 to the k, right? So what is this? Is the smallest L such that 3 to the k divides 10 to the L minus 1. Okay, so it means it's the smallest L such that I take the valuation of 10 to the L minus 1, it's greater than or equal to k. But what is the exponent lemma going to tell me? It's going to say that this guy is equal to the valuation for this plus the valuation for L. So it means that I need the valuation of L to be at least k minus, in this case, 2. So the smallest of this number will be 3 to the k minus 2.
Mm.
Does it make sense?
Yeah.
Yes.
So when it's not divisible by P, we choose a value of, for example, A to the L, the
Yeah.
minus 1 that is divisible by P, the same way we did with 2 and 4.
Yeah. Right. Yeah. So yes, exactly. But let me, so in the case, okay, so what case do we do here? We just did the case where D is 1, right? And in that case, what is it? We show that like basically, okay, what you get this P to the K minus R, right? And then if the X of K is too small, it's just 1. Yeah. So Karam, does it make sense what like in the case when D equals 1 that this why this formula would be true? I just want to make sure that you understand when D is like the case we just did, when D is 1. Yeah.
The case that B is 3.
So yeah, P is 3, but I'm sort of saying in general, what was the point here? The point was that D is equal to 1. That the number we started with, 10, is already 1 mod 3.
Yes.
Right. So
Yes,
in that case, it's like
obvious.
this. Okay, yeah, okay. Okay, great. Okay, good. Okay, so the thing that you have to understand is when it's not D is not 1. But it's very similar, right? So when D is not 1, what does it mean? So yeah, so if we start with what if D is not equal to 1, right? So we want to understand the order mod P to the K of A, but A is not already 1 mod P, but we know what? We know, okay, so this is going to be the smallest L such that P to the K divides 3 to the L, not 3, sorry, A to the L minus 1. But if P to the K divides A to the L minus 1, then P divides A to the L minus 1, which means we can write L is equal to D times L prime. So, okay, then what we want P to the K divide, so we want smallest L prime such that P to the K divides A to the DL prime minus 1. But what is this? This is A to the D, the L prime minus 1. And now this one, A to the D, is congruent to 1 mod P. And so we can use the lifting the exponent. Right, so it's like use lifting the exponent on A to the D. Right.
Are we allowed to use lifting the exponent without any proof?
It's a good question. Yeah. Okay. I don't know. I think so. Okay. Okay. Maybe remind me next time, and I'll have an answer for you. I think you can, but maybe sometimes it's better to give a proof. But okay, maybe I won't answer because actually I'm not exactly sure. Yeah. Yeah. Okay, so okay, yeah, so does it make sense how you can deduce the case for when A is not 1 mod P from the case when A is 1 mod P?
Yeah.
Yeah. Okay. All right, so that maybe concludes what I wanted to say about order modulo a prime power. But there's still something I wanted to say just about doing arithmetic modulo a prime power. So there's this problem here. Okay, I think I have it copied somewhere else. Let's see. It's here, yeah, okay. So the problem is like this. So you have an integer polynomial and you have a prime p, and so everything is modulo prime p. And you're given that when I look at the values of the polynomial, the p of 0, p of 1, all the way to p of p squared minus 1, mod p squared, these are all distinct. Okay, so every residue class is occurring once. And okay, also let me remind you, So the way polynomials work is that like I don't know if you covered this, but like P of X is congruent to P of X plus N. Or okay, what am I saying? Like if X is congruent to Y mod N, then P of X is congruent to P of Y mod N, right? This is for any integer polynomial, right? Because like what is P? It's like you're taking powers and sums, and both of those you can do mod N, right? So okay, so what it's saying that okay, this you look at the values of the polynomial, okay, it repeats every P squared mod P squared, and you see every single residue class exactly once. Okay. So it's a very nice statement. And the problem is, okay, if it's true for P squared, you want to show it's also true for mod P cubed. So you want to show that if all these, P squared values are different mod P squared, then want to show it's also true for mod P cubed. So I think that P cubed minus 1 values, they're all different to mod P cubed. Any ideas where we can make this? So one point is that if I write these values mod P cubed, or sorry, yeah, the values P of 0, P of 1, I can write them in some big table like this. So I go P of 0, P of 1 all the way to P of P squared minus 1, and then but here I put P of P, P plus 1, P of, sorry, no, not P squared rather. Okay, so P of P squared plus 1, P squared, maybe not what, I call it 2P squared minus 1, right? So here. Okay, so I'm grouping that into blocks of P squared. And there's going to be, the last one will be P of P squared minus P of P squared minus P plus 1, all the way to P of, sorry, that's not right. P of P cubed minus P of P cubed minus P plus 1, all the way to P of P cubed minus 1. So I grouped the values into like P rows and P squared columns, yeah? So now, if I look at two values that are in different columns, so if I have two values that are in two different columns, I know they're going to be different modulo P squared, so they're also different modulo P cubed. So the problem really, it amounts to like looking in the columns and showing that the values are, like the residues are different in each column. Does it make sense? So I'm stating a reduction, which is solving the problem is equivalent to showing that in each column, the residues are different modulo P cubed. Does it make sense what I'm doing here?
Yes, but I think in the last row we should have b of b to the 3 minus b squared.
Yes. The first term is P cubed minus P squared. Yes. Thank you. That's
Yes.
right. Yes.
And then
Yes,
we have
that's right.
Yes, the second one we have should have b
yes,
squared.
thank you. Yes, thank you. Okay, good. So we have this, and now we want to understand the difference between these numbers, right? So I want to say it's kind of similar to a step in the previous problem. So in the previous problem, we had a step where we had what? We had this expression here that we wanted to understand, and we knew that A and B were equal mod P, but maybe not mod P squared. And so we did this kind of a substitution, and it was very helpful because we were able to use this binomial theorem. And it's the same, it's a very similar situation because what do we have here? We have in each column, we have a bunch of numbers that are equal mod P squared, but they're different mod P cubed. So since these are all equal mod P squared, we know that in each column, the values are equal mod P squared. But we want to understand that, or we want to show that since they're different mod P cubed, the values are also different mod P cubed. So any ideas how we could do that? Let's formulate the problem, right? So the problem is we have what? We have A, we have A and B, where A is congruent to B mod P squared, but A is not congruent to B mod cubed, P cubed, and we want to show that P of A is not congruent to P of B mod P cubed, even though they're equal mod P squared. So the thing to do if we're following what we did before is, okay, we know A and B are equal mod P squared, but not mod P cubed. So we write A, we can write maybe B is congruent to A plus K times P squared mod P cubed, where K is like 0, 1. Oh, sorry, not 0, definitely not 0. Like 1, 2, or something, P minus 1, one of these. Does it make sense?
Yes.
And now we want to compare, okay, with this substitution, how do we compare the values of P? Now, from before, what do we have? We have this lemma from before that I called it the important lemma, but okay, let's recall what it says. So it's that if I look at A plus okay, it's a little bit different, but let's take A plus KP squared, and let's raise it to the power of M. Okay, so it's what we were doing before, right? Okay. So what will happen when we expand this? We'll get A to the M, and we'll get M, choose 1, which is just M. So we'll get M times A to the M minus 1, KP squared. And then everything else will actually vanish mod P cubed, right? Because all of this stuff will be divisible by P to the 4th. So it's actually just going to be 0 mod P cubed. So the conclusion is what? The conclusion is that if I take A plus KP squared to the power M, this is just A to the M plus m a to the m a minus 1 times kp squared mod p cubed. Okay. Yeah, does it make sense?
Yes.
So, but we can use that, right? Because we want to compare what P of A and P of B. And P is just a sum of a bunch of powers, right? So let's write P is equal to Cn x to the n plus Cn minus 1 x to the n minus 1 plus C0, right? So now what? So yeah, so let's see. What does it mean? We can erase this stuff here. Okay. So now what? Now if we go back to the problem, we want to understand the difference between P of A and P of B. So when we look at P of B, it's going to be what? Let's write it as a summation. So we'll have sum over all the m's of Cm times A plus kp squared to the m. Will be m equals 0 to n. And what is this? This is mod p cubed. We have what? So you have Cm, and we have Cm a to the m, and we have Cm m a to the m minus 1 k p squared. It's all mod p cubed, right? So the point is this first term is just p of a. Like when we add up all this first term, m equals 0 to n, that's just p of a. So this whole thing, it is just you have p of a, and then we have this extra stuff. And in the extra, we can pull out what? We can pull out kp squared, kp squared, and then times sum m equals 0 to n of Cm times m times a to the m minus 1. Okay. Does it make sense so far?
Yes, but how can we prove that this sum is not congruent to 0 mod B?
Ah, good. So we want to show this sum is not 0 mod p, right? Because good. So you want to show the sum is not 0 mod p. Yeah, I mean, okay, we want to show that the second term, so yeah, we want to show that this whole thing is not 0 mod p cubed, but we already have a p squared there. So we have to show that p does not divide this. Okay. Yeah, so we want to show p does not divide this sum. So we can do this, but before we go on, does anyone recognize what this sum is? It actually has, there's a nicer way to write it in terms of this polynomial. So this thing, m a to the m minus 1, it's a
Divided by
derivative.
A?
Sorry?
Yes. Yes.
It's a derivative. So it's funny.
Yeah.
This is this guy, I mean, it's not really, I don't know if it's important, but this is the derivative of p at a.
But
It's not important,
how could
but
this
it's true. Hello?
how could we prove that? But how could this help us? Help us.
So it's not going to help us. I don't think it's really going to help us. That like the fact that it's a derivative will help us. It's just I wanted to point out that what this expression is. It's not a random expression. It actually has a meaning. It's the derivative. No, I don't think it'll help us, but okay, it's kind of interesting. Okay. Yeah, but really we want to understand this expression, right? We want to understand that it's not divisible by p. So let's rewrite our problem. Our problem now is what? To show. Yeah, so what do we want to show? Therefore, suffices to show for all a that sum from m equals 0 to n, dm m a to the m a to the minus 1 is not congruent to 0 mod p. Okay, that's what we want to show.
But when we have m equal 0, we have the term will be, it will be 0. I think that
Yeah,
we have some. I thought that we could have some negative powers.
no, we won't have negative power. Yeah, you're right. So it's when you take the it's like a derivative, right? The constant term becomes 0, right? So okay.
Yes.
Yeah. But now, okay. Let's think a little bit about what happened. So we wanted to understand what we had is what we have two numbers that are equal mod p squared but different mod p cubed, right? And we wanted to understand the difference between the polynomial values. And what we understood is that the difference, like p of a minus p of b, is this guy, right? So let's write it once more. We have, okay. If a is congruent to b mod p squared, and then particular it means you write b is equal to a plus kp squared, then the difference between p of a and p of b, when we consider mod p cubed, right, is equal to, well, this kp squared times this sum, right? M equals 0 to n of cm m a to the m minus 1, like this, right? Okay. And now we want to show that this guy is not 0. But here's the trick. So the trick is we skipped something, right? Like we went from mod p squared to mod p cubed, but we should actually, when we started, we should have really gone from mod p to mod p squared. So the fact that p of 0, p of 1, that these are all, all distinct mod p, right? What does it mean? It means if I take a and b such that a is congruent to b mod p, but a is not congruent to b mod p squared, how do I understand their difference? So by similar argument, their difference is going to be mod p squared now, is going to be kp times the same sum. Okay, because what will change? I mean, when you do the argument here in the lemma, everything will be the same except this this p squared will be a p. So this will, instead of being kp squared, it'll be kp. And so the difference will be the same thing with kp instead. Okay. So it means that if I take two values that are, where did they go? Yeah, if I take two values like this, so that they're different, that they're the same mod p and different mod p squared, their difference is exactly recorded by this expression.
And we know that
So,
it's not divisible by p for a fact, so
Yep, exactly. We know that this guy is not divisible by, this expression is not divisible by p because by assumption, the values are different mod p squared. So it tells us that they're also different mod p cubed. Does it make sense?
yeah, yes.
Yeah, so it's very clean thing. It's the main thing is, is this realization that when I want to understand this kind of difference for two things that are equal mod one power but not the next power, it just has to do with the derivative. That's it. So yeah, so it only has to do with the derivative, right? So yeah. But kind of you already saw this, right? Like it's what? It's like we kind of already saw this because what is lifting the exponent about? It's like about the polynomial x to the n, right? And okay, so you can actually understand lifting the exponent as being related to this for polynomials that are just x to the n. Okay. Okay, so any questions about this problem? Hello? Oh no, in fact.
Yeah. I got it.
Okay, good. Sorry, I have to reshare my screen share stopped. Okay, so I want to do one more problem. Yeah, so this is what? So what's the problem? The problem is, okay, yeah, let's do this one. So yeah, okay, so I want to do some problems that are from previous IMOs. So yeah, let's see. Yeah, so let's look at this one problem here. So okay, so find all positive integers a and n so that n divides a to the n plus 1 minus a to the n. A plus 1 to the n minus a to the n, right? Okay, so so any ideas where can we start?
maybe we can start by reducing it a bit.
Okay.
Using the binomial expansion, we can get rid of a to the power of n, and also we know that at least two terms will have n as part of the constant.
Yeah, okay, so we can do it like this. and this one goes away, right? So yeah,
know
so
we can remove two terms again, which are n choose 1 and n choose n minus 1.
so we can remove 2, and we have left with
n choose
yeah,
2, n choose 3, up until n choose n, except for n choose n minus 1.
so I guess we can group them like this, right? So yeah. Okay. I think.
We can also group each n over k and n over n minus k.
Mm-hmm.
I'm not sure if this is gonna work. I'm just trying things out.
Yeah. So it's a good idea. I don't know if it'll work either. Oh yeah, each individual term is not going to like so okay, if n was prime, for example, okay, then we can use this, right? Because if n is prime, then all of these are divisible by p. Right? If n is p, then okay, and then it's not possible, right? It's like you have this one leftover term and it doesn't work. Okay. But maybe n isn't prime. I mean, in that case, I don't know, it's very hard to deal with these binomial coefficients. But okay, somehow this is, this expression here, right? This okay, what you have what a plus 1 to the n is congruent to a to the n. It's saying something about orders, right? It's what is it saying, right? It's saying oh, okay. Here's one thing. If a is coprime to n, then this statement is equivalent to a plus 1 over a, which I understand as a plus 1 times a inverse mod n, is to the power of n is congruent to 1 mod n, right? So if a is coprime to n, which maybe it's not like you're just solving like x to the n is 1 mod n, right? Because this is like you can okay, x is congruent to a plus 1 times a inverse, and then you're just solving x to the n is congruent to 1 mod n. So you're saying can there be a number whose order mod n is a divisor of n? Does it make sense?
Wouldn't that only work if n is 2?
What do you mean?
Because we need to have that 5n should divide the order, and we know for a fact that n minus 1
So
is
we know
also
the order divides phi of n, not the other way, right?
yeah, and also divides n minus 1.
Why n minus 1?
Because by Fermat's little theorem. Oh, that's only for primes, not for co-primes.
So if n is prime, then so we know the order divides n, and if n were prime, it would also divide n minus one, and then we would be done, right? But it's not quite the case. But okay, let's okay. Somehow,
we
I
can
said
why don't we consider the primes that divides n?
great, yeah. So let's do that. So let's just let's instead of working at all mod n, that's kind of hard because phi of n is kind of hard to get a handle of. Let's just work one prime at a time. Okay, this is a very good technique in number theory when you get stuck, is to work one prime at a time. Okay, so let's suppose p divides n. P divides n. Okay, so now what we have a plus 1 to the n is congruent to a to the n mod p. Okay, so now what? So one thing it's immediate is you cannot have both of these divisible by p.
Why?
Because they differ by 1, right? A and a plus 1 are they're coprime, right? So they cannot be divisible both by p. So it means neither is divisible by p, so we can take inverses. It's okay, we can take inverses. We can say x is equal to a plus 1 times a inverse. Okay, mod p. And it tells us that x to the n is congruent to 1 mod p. So, okay. So there exists a number, right? So there's a number whose order divides order sub p of x divides n. Okay. And we also know the order divides p minus 1. Okay. Now,
actually, I think we can say that n equal k times p to the x, where k is not divisible by p.
yeah, so we say n is equal to k times, let's not write, let's like y. Let's write p to the d. Maybe. I already used x, so let's do d. It's okay.
Basically, so we have a plus 1 to k times b to the d is congruent to a to the power of k times b to the d mod b.
Using a plus 1 to the k times p to the d is congruent to a times k to the p to the d, yes?
And so we have a plus 1 to the k is congruent to a to the k mod b by Fermat's theorem.
Yes, it says a plus 1 to the k congruent to a to the k mod p, yes. Okay.
And that is better information.
Yeah, it's a good information now.
So we have the order divides k of x.
Yeah, but actually we knew that from this statement because the order divides n. The order cannot divide p because it's a factor of p minus 1.
Yes.
So it has no factors in common. It has no powers of p. So that it divides n meaning it also divides k. So actually we knew that from this kind of thing here. So this will give us that the order divides K. But okay, so now I'll pause a little bit. So far, what we've been using theory. The next step is what makes this an IMO problem and not just a theory problem. So these two facts by itself, it's not so easy to use, but we can do something clever, which will make this fact actually very strong, right? So we know the order divides n, and we know it divides p minus 1. So it divides the GCD, but we have no control over the GCD. But there's something very clever we can do that will give us a lot of control over the GCD.
We can just take the smallest p.
Yes, this is so we call it extremal principle, right? So you say, okay, I want some control. I take the smallest p that divides n. Why is that useful? So yeah, so we take so suppose p divides n, and p is the smallest prime dividing n. So what does it mean? So now when we look at n, all the factors of n are more than p. When we look at p minus 1, all the factors of p minus 1 are less than p. So there's actually no common, their GCD is 1 because of the assumption.
So the
Does it make
order
sense?
is 1.
The order is 1, exactly right. So if we take the smallest prime, it means that the order, oops, I don't want that one. So yeah, so under the additional assumption that it's the smallest prime, we get that the order is 1. So what does that mean though?
That means that x to the 1 is congruent to 1 mod b.
X to the
so
1 is 1 p. Yes.
So we have a plus 1 times a inverse is 1 mod b. And so we have a inverse is 0 mod b, which is a contradiction.
Yes. Yep, exactly right. So we get to that this is congruent to 1, and that's a contradiction. Yeah, because that cannot work, right? Because it means 1 plus a inverse is 0 mod p. So it doesn't work. So it means, so we get a contradiction. So it means that n cannot have any prime factors at all. So n is 1.
No.
Does that make sense?
Yes.
Yeah, so the only solution is when n equals 1, and when n equals 1, yeah, of course it's an integer, right? So the only solution is n equals 1. Yes, it's a very nice problem. It uses theory and it uses this one trick, okay? You have to understand that, yeah, we work modulo a prime, but we work modulo a special prime. We work modulo the smallest prime that divides n. And then we get something really strong. Okay, so any questions about this? So, okay, I guess before we break, I want to do this last problem. It's very, I think it's maybe similar to the previous problem, but okay. It's very nice. So yeah, so what is this problem? It's so you want to find again all pairs of positive integers with p now prime such that x to the p minus 1 divides this one, and we have this weird assumption that x is less than or equal to 2p. So okay, so when you see a problem like that, there's sort of a natural thing. You want to understand the divisibility condition. And then this x less than or equal to the p, probably what we'll do is when we follow the problem, we'll realize it was necessary to make for one of the steps, right? So basically, what I'm saying is, just don't really worry about this for now. It will become clear later why the problem writer added it. Let's work with the important condition, right? So x to the p minus 1 divides p minus 1 to the x plus 1. Okay, so what can we do?
We consider the prime that divides x.
Great, so we say consider q that divides x. So what we have now, we have, well, okay, we have, sorry. Yeah, okay, so okay, so it means that p minus 1 to the x is congruent to minus 1 mod q. Actually, it's true mod q to the p minus 1, but let's first work mod q, and then if we need more information, we'll go mod q squared all the way to mod q to the p minus 1. But first, let's start with mod q. Okay, so what does this tell us?
That the order of b minus 1 mod q divides 2x.
Divides 2x. It divides 2x. And, in fact, from previous things, we know a little bit more. We know that the order is even, and we know that x is an odd multiple of half the order, right? You guys remember this. This is some, okay, we deduced this before, right? But okay, so that's a little bit more technical condition, but at least we know this, and we know a little bit more, and we'll use it if we need to. Yeah. Okay.
And also
we know
also,
the order. We know the order divides q minus 1.
Yes. Okay.
So it should divide the GCD of 2x and q minus 1.
Great. So it
And
divides
if
the
we
GCD.
suppose q is the smallest prime dividing x, then we get q equals 2. No, q equals 3 or 2.
Yeah, so it's the same trick as before, right? So we consider q dividing x, and we now, so yeah, so in order to get more information, we assume and suppose q is the smallest prime dividing x. Okay, so now what does it tell us? Since it's the smallest prime dividing x, we can look at these numbers at 2x and q minus 1. So q minus 1 is a number that's a product of primes less than q. And 2x, well, okay, I don't know about the 2, but I know about the x part. By assumption, the x part only has prime factors more than q, or equal to q. So the GCD here is, well, it's either 1 or 2, and yeah, so it's either, let's just say, it's either 1 or 2. We'll decide which one soon, but it equals 1 or 2.
Oh, yeah, it's 2.
Yeah, so why isn't it 1?
Because we know that p minus 1 perfect is congruent to minus 1.
Yep, exactly.
would
It's this
yeah.
the secondary condition we wrote here, right? We know this order should be even. So the fact that p minus 1 to the power x minus 1, it tells us that it's not 1. It's not 1. It must be 2, actually. So it's actually 2.
or maybe we could have q is 2, because if we have we can have that the order is 1, and we have 1 is congruent to minus 1, and so q is 2.
So we can have q equals, well, okay, so let me understand. So the conclusion here, so the GCD is it's 1 or 2. So yeah, you're right. It's if q is odd, it's 2, and if q is even, it's 1. But that's not how I decided that it's between 1 and 2. The way I decided is that the order divides the GCD. right? So I didn't mean to write equals. I meant to write divide. So the order here, it divides the GCD, right? Now, but the point is, okay, so the order is 1 or 2, but it cannot be 1. Why it cannot be 1? Because I know the order is even. Or like, okay, if the order was 1, I couldn't have this thing, right? I cannot have p minus 1 to the something equals -1.
But we could have if Q is 2.
But if Q equals 2, this GCD is 1. So that would force the order to be
Okay.
1. It makes
Okay,
sense?
the other, yes, we could have the GCD is 1 and the other is 1.
But then the order is not 1, because if the order is 1, you can't have this.
But I'm assuming that the Q is 2 here. So this is possible.
You're right. You're right. Yes, you're correct. You are correct. You're right. I did not. Okay, you're right. So we kind of very good. Okay, no, this is a good point. I didn't realize. Okay, good. This is a good point. Yeah. So okay, thank you. I didn't understand this before. So yeah, there are two things that can happen here. You can have Q odd plus. Okay, so we can have. Yeah, you're right. You're right. So it's a good point. So we can have two cases. One we can have is Q is odd, and Q is odd, and the order mod Q of p minus 1 is 2. Or we can have Q is 2, and then the order, okay, well, there's nothing to really say, but okay, then the order is 1, but it's kind of just, yeah. Okay, good. So now let's see if these make sense. Okay, so let's do some parity checks. So we look at this expression. So if p is okay, so let's see. If p is 2, yeah, if p is 2, this expression is not if p is 2, this is not very interesting. It's 1 plus 1, it's 2, and x has to be 1 or 2 or something. Okay, so if p is 2, it's not that interesting. Let's assume p is more than 2. So if p is more than 2, this number is odd, which means x has to be odd. Yeah?
So Q could not be 2.
Yeah, so q cannot be 2. Okay. Yeah, so good. So let's let's write it down. So okay. So case 1 is p equals 2, and then I think it's x equals 1 or 2. Something like this, I don't know. Okay, that's not very interesting. So the other case is p is more than 2. So then x is odd. So then we're in this first case, which means that q is odd, and the order mod q of p minus 1 is equal to 2. Okay. Okay, so what does it mean? Yeah, so let's see. The order, what does it mean? It means what? So it means p minus 1 is congruent to minus 1 mod q, right? I think that's what it means, right? If something has order 2, it has to be a square root of 1, which we know modulo prime has only 2 solutions.
Yes, and so Q equal B.
Yeah, so in particular, q equals p. So it tells us the smallest prime factor of x is p.
It's a contradiction.
It's not a contradiction, right?
Since x is less than or equal to 2B.
So yeah, there's one, we could have x equals p.
Yes.
Yeah, so it's not a contradiction. Yeah. Yeah, so it means x equals p, yes. Okay. So now it's actually much simpler, right? We know x equals p. So great. So we actually just eliminated one of the variables. X equals p. So actually, you know, in fact, I think, oh, okay, whatever, x equals p. So now what? So now we have p to the p minus 1 divides p minus 1 to the p plus 1. So we have p to the p minus 1 divides p minus 1 to the p plus 1. Okay, and this is maybe looking a little bit better. What do we do with this? So
B is congruent to minus 1 mod B. We
yeah,
can use the
so
lifting exponents theorem.
exactly, right? So yeah, so p minus 1 is congruent to minus 1 mod p. So we just use lifting the exponents. So we say vp of p minus 1 to the, so I guess, yeah, we had p was odd, right? So p minus 1 to the p minus negative 1 to the p is equal to vp of p minus 1 minus negative 1 plus vp of p. So the first one is just 1 plus 1 is 2. We get 2 powers of p in there. Okay, so it tells us that p minus 1
B
is
minus
less than or equal to 2.
So B is 3.
So p is 3. It's only p is 3. So what are the solutions? There's p equals 3, x equals 3, and there's the solution when p equals 2, which I think what it means what? X equals probably 1 and 2, I guess. Yeah. There's 3 solutions. Yeah. Okay, so that's the problem. Any questions? Okay, so okay, it's getting pretty late, but do you guys know, there was one more thing I wanted to cover. Do you guys know what how to deal with fractions mod p? Like
Yeah, they're just inverses.
yeah, they're just inverses. Everything makes sense. So as long as your fraction doesn't have a p in the denominator, everything is completely okay. So like you can add fractions, you can do everything. So you can do any arithmetic you want with fractions. The only condition is no p in the denominator. Then you can do whatever you want, and everything is okay. So yeah, okay. So like when you have a problem that says show that p divides the numerator, it really just means you want to show that a over b is congruent to 0 mod p, and that's it. Okay. Yeah, so hopefully that's something you guys are familiar with. If not, just message me and I'll send you some kind of reading. Okay.
But I think here we assume that B is not divisible by 0.
Should
B
that
is
what?
not B is not divisible by B, I mean.
Yeah, so you need to, I guess you need to show, but it's okay. Like anytime I have some fractions that are not divisible, that don't have p in the denominator, then if you add them, if you multiply them, they won't have any p in the denominator. Just you can check. Yeah. Okay, so yeah, so the homework is what it is, and I guess there's something I didn't add. So okay, so there will be something I wanted to add to the homework. It's called Hensel's lemma, so I'll add that later. But when you see Hensel's lemma, you'll understand that it's basically the same technique as we used in this problem 8, problem 7 and 8. So this really problem 8. Okay, so this idea we use in problem 8, there's a very nice result that comes out of it called Hensel's lemma. So I'll add it to the homework. And right, so that's it for today. Any questions?